Okay, this is worksheet 10. I'm going to go over these problems. We're on number 1. And what it says is we have 3 flasks. They are each 5 liters in size, so I'll try to draw them about the same size. And that each contains 4 grams. And they are all at 0 degrees C. And that the first flask contains hydrogen, the second flask contains helium, and the third flask contains methane. And it says rank the flasks from highest to lowest in terms of pressure and then density. So let's look at pressure first. So pressure of a gas inside a flask is caused by collisions with the walls. And the more particles you have, the more collisions you have. So we know that the number of moles or number of particles is directly proportional to the pressure. So if we can figure out the number of moles of each, we can answer this question. So if I have 4 grams of hydrogen, what I know is each weighs about 2.0 grams. For 1 mole, that's going to give me 2 moles of hydrogen. We do the same thing with helium, 4 grams of helium, and each is 1 mole is about 4 grams. That's going to give me about 1 mole of helium. And if I have 4 grams of methane, that molar mass is going to be about 12 plus 4 is 16, or about 0.25 moles of methane. So I'm going to have the most particles of hydrogen, so I'm going to have more collisions, twice as many collisions with hydrogen as I have with helium, and 4 times more with helium than I do with methane. So I'm going to, the highest pressure is going to be from hydrogen, then helium, and then methane. Now that's about density, but what this told us was that all of these had a volume of 5 liters. So the density is mass over volume, and in all cases we have 4 grams over 5 liters. So all of them will have equal density. Okay, this is problem number 2 with worksheet 10. What it says is we have 40 liters of nitrogen, and it's measured at 1.23 atmosphere and minus 42 degrees Celsius. So this looks like a Pivnert problem. I have a gas. I know 3 things about it. So what I know is I have 40 liters, 0.0 liters. I have 1.23 atmospheres. I have 42 degrees C, and I want to know how many grams. And I also know that it's nitrogen. Nitrogen is diatomic. So if I think about PV equals nRT, I know that if I get N, it's going to help me figure out mass. So I'm going to solve for N, and to do that, I'm going to isolate it by dividing it by RT so that it cancels, but I've also got to divide this side by RT. So this is the equation I'm going to use to solve for N. So my pressure is 1.23 atmospheres. My volume is for 40.0 liters. My R, because I'm using atmospheres and liters, is 0.0821. And my temperature is 42 degrees Celsius, so 273 plus 42 is 511, 315. Whoops, it's minus 42 degrees Celsius, so that's 273 minus 42, which is going to give me, over here, 231. So if I multiply that out, I end up with 2.59 moles. So what I know is moles of anything is equal to the grams divided by the molar mass. And what I know is I have 2.59 moles, and that's going to be equal to the grams over the molar mass. And because it's nitrogen and I've got 2 of them, it's going to be 28.02. So if I solve for grams, it's going to be 2.59 times 28.02, which gives me, if 3 sig figs is 73 grams. Now we have a gas-filled weather balloon with a volume of 65 liters is released at sea level conditions of 745 torr in 25 degrees C. The balloon can expand to a volume of 835 liters before exploding. The balloon rises to an altitude at which the temperature is -5 and the pressure is 0.066 atmosphere. The question is, will the balloon explode? Provide evidence to support your claim. Okay, so this looks like a problem where temperature and pressure are going to change. So this is not an ideal gas law problem. It's a combined gas law problem. So what we want to do is look at, we're starting with 65 liters. So I'm going to put 65 up here. And 745 torr. So this is pressure. So the torr is the same as millimeters of mercury. In 25 degrees C, 273 and 25, let's get that in Kelvin, that'd be 298. Okay, and it says the balloon rises to an altitude at which the temperature is -5, so that'd be 273 minus 5, that's going to be 268, and 0.066 atmospheres. So I have torr here, I can't use atmospheres and torrs. I've got to convert one to the other, so I'm going to make this torr. So I have 0.066 atmosphere, and what I know is 1 atmosphere is 760 torr. So this is going to give me torr of, let me see, torr of 50.2. Okay, so now I have my volume, my pressure, and my temperature. So I'm trying to look at what happens to volume. So I got my 65 liters. Now my pressure goes way down here, which means my volume will go up. So I need 745 over 50.2. My temperature goes down, which means my volume will also go down. So I want 268 over 298. And if I multiply this out, I get 965 liters, which is greater than 835 liters, which is the volume at which it will explode. So we are going to explode. Okay. Okay, so we're still on worksheet 10, and we are on number 4. So it says we have a gas whose behavior resembles ideal gas, and it's got 2,000 milliliters, 27 C, 120 kPa, and the question is how many moles are in the sample. So this is a Pivnert problem because we're not changing conditions. So we have, we're trying to solve for moles, so PV equals nRT. So we're trying to find moles, so we're going to divide both sides by RT to isolate N. That will cancel out, so we're going to use PV over RT. Alright, so our pressure is 120 kPa, 120.0, times our volume, which is 2,000 milliliters. Now my R's all require me to have L, use liters, so 2,000 milliliters. And I know 1,000 milliliters is 1 liter, so this is going to be 2 liters over R. I'm going to, because I have kPa's here, I've got to use 8.31. And T, my temperature is 27. If I add 273 to that, I'm going to get 300. So I do all this, and I multiply it out, and I end up with 9.74 moles. Now it's also asked how many molecules, so I take that 9.74 moles, and I know 1 mole of anything is Avogadro's number, 6.022 times 10 to the 23rd, and I get 5.9 2 sig figs times 10 to the 24th molecules, and that's Bobo in the background. I hope he's not bothering you. Okay, let's move on to number 5. Number 5 says a quantity of gas has a volume of 120 liters when confined under a pressure of 700 millimeters of mercury at a temperature of 20 C. Assuming temp remains constant, at what pressure will its volume be 30 liters? And it gives us a centimeters cubed to milliliters conversion. Okay, So here we're changing conditions. So this is a PVTN kind of problem. So I got 120 liters, pressure of 700 millimeters of mercury, and a temperature of 20 C, and I'll just go ahead and make that 293 K. Temperature is constant, so this doesn't change. At what pressure will its volume be 30 liters? This is a pretty simple problem. I don't really even need this conversion, right? Okay, so I'm trying to figure out the pressure, so I've got 700 millimeters of mercury, and what I got to look at is what volume factor I want to use. So my volume has gone down, and if my volume goes down, my pressure is going to go up, so I need 120 over 30, and when I do this, I get 2,800 millimeters of mercury. Okay, that's 2 sig figs, that works. Okay. Let's go on to number 6. It says in an airplane from San Diego to Boston, the temperature inside is 5544 liters. Well, the temperature and pressure at 25 C, 942 kPa. How many moles of air are present? So this is PV equals nRT. I'm solving for N. I divide both sides by RT, so this cancels, but I gotta do it here. So my equation is PV over RT. My pressure is 94.2 kPa. My volume is 5,544 liters. My R, since I'm using kPa, is 8.31. My temperature is, this is 273, that's going to be 298, 298. If I multiply this out, I get 210 moles of air, which is 2 sig figs, just like my temperature. Easy one. Let's take a look at number 7. Whoops. Number 7 says a gas sample has 0.719 grams, occupies 0.570 liters, gives a temperature of 281 K, and the pressure is 1,094 millimeters of mercury. What is the molar mass? And therefore, what is the gas? Okay, so this hint is to solve for moles first. Alright, so I'm going to use that same formula I just used. N equals PV over RT. My pressure is 1094.4. PV, my volume is 0.570. My R, because this is millimeters of mercury, whoops, I gotta change that. I can't use millimeters of mercury because I don't have an R that matches. 1094.4 millimeters of mercury. And what I know is 760 millimeters is 1 ATM. So this is going to give me 1.44 ATM. So I'm going to start this over. 1.44 is my pressure. My volume is 0.570. I'm going to put that over R, which is 8.31, because I'm 0.0821 because I'm using ATM. And T is, what did we say? T is 281. I'm kind of making a mess of this one, aren't I? I multiply all that out, and I get 0.0356 moles. Okay. Now what I knew was I had that many grams. Okay. So I have moles and I have grams. And what I know is moles are equal to grams over molar mass. So 0.0356 is equal to 0.719 divided by molar mass. So I'm solving for this. So molar mass times 0.0356 equals 0.719, or molar mass is equal to 0.719 divided by 0.0356. This gives me an answer of 20.2. And I look at my periodic table, and what I find is this is neon. Neon has a molar mass of 20.2. Okay, let's pause for a sec. Okay, so we are on number 8. It says we have a sample of a gas, 30.8 liters, 52 degrees C, 149 kPa, calculate number of moles. This looks pretty straightforward as a pivnert. I'm going to use the formula that we just finished using, N equals PV over RT. My pressure is 149 kPa. My volume is 30.8 liters. My R, because it's kPa, is 8.31. And my temperature is 52 plus 273. And that's going to give me 325. I multiply this out and I get 1.7 moles. Pretty easy. Let's take a look at number 9. Question is, what pressure is exerted by a certain number of moles in a certain volume at a certain temperature? Okay, again, this should be pretty straightforward. So I've got PV equals nRT. I'm solving for P, so I get it isolated by dividing by V. So this is the formula I'm going to use for solving. So my moles are 0.625. My R, let me see, I'm going to get my pressure in ATM, so I'm going to use 0.0821. My temperature is 273 minus 24 is 249 over my volume, which is 45.4 liters. If I multiply that out, I get 0.281, and because I use 0.0821, then my units will be atmospheres. Okay, that's going to do it.